Hello, everybody. Just a few more minutes. Hopefully, one or two more people will turn up. I've actually produced a PowerPoint for this. I hope you're impressed because I wanted to do something that was fun. And there were so many things that I wanted to show you. So I've made a PowerPoint. Oh, it's death by PowerPoint. I'm sorry. Okay, it's the 16th of the 10th. Cool. Well, I hope you are, all of you, having a good day. One more minute. Right, go to here and share my screen. Oh, and that's the end, not the beginning. Slideshow, start from the beginning. Cosmology, it's very exciting. Oh, I can't see if anybody else is arriving. Right, well, I make it 7 o'clock, so I'm just going to go with it. Perhaps I'll get my list of participants up. Put that over to one side. Hopefully that's not going to impact your view. I'll get my chat up as well. Also over to one side. And again, I hope it's not going to impact your view. Right, tell me if it does. Okay, I am going to give it a go. Starting now. So cosmology, here we go. So there is a cosmological principle, and the cosmological principle is that the universe is homogeneous. That means it's the same everywhere. Isotropic. That means it's the same in every direction. So it's not just uniform everywhere, but if you look in every direction, it looks the same. Okay, it's not, there's no pattern to it, nothing. Okay, it's the same everywhere. And the laws of physics are universal. And I've put throughout space and time because I wanted to make it clear that we assume that the speed of light has been the same throughout the entire existence of the universe. We haven't got any evidence for anything different to that. And so we've made that assumption, and it's a principle. So, but it is an assumption. We haven't got evidence for it. So we have to make these assumptions. I mean, it seems weird to think to yourself, well, can we be sure that the speed of light has been the same since the beginning of time? Well, how are we going to know? I mean, the truth is we can't know. So it's an assumption, and that is part of the cosmological principle. So, and it's the same everywhere throughout space, and the same everywhere throughout time. And and we've assumed that physics, the laws of physics, are the same. So gravity was gravity even at the very beginning, and electric charges were the same, and etc. etc. What wasn't there at the beginning were whole atoms. Oh, okay. So but there you go. That's the cosmological principle upon which we base our cosmology, which is the study of basically everything, which is kind of cool. I think it's very cool anyway. Right. Okay. So now The main part of you, most of you are doing either the AQA, in which case the bit that you're the people who are interested in this are doing the astrophysics option, which is actually most of you, or you're doing OCRA. I've got one person, I think, doing Edexcel. I've got one person doing OCRB, and there are elements of this in both of those. I've got one person doing the IB, and that has elements of astrophysics and cosmology and the Big Bang and stuff in it as well, and the Doppler effect. So everybody that is doing a space and time, it is the Doppler effect is part of the things that you need to know. Okay, so here is the Doppler effect, right? Now the Doppler effect is where when the police car or fire engine or something is coming towards you, it gives you a different pitch sound when it's going away, and that's because the waves are squashed when they're coming towards you if the source is moving, and stretched when they're going away if the source is moving away. So and that's it leads to a change in pitch if it's sound, but it leads to a change in color if it's light, and it doesn't actually matter if it's visible light or not. If the source is moving away from you, the waves are stretched, and if it's moving towards you, they are squashed. But we refer to it as redshift if they're stretched, because visible light gets moved towards the red end of the spectrum. So this is redshift. And we've got, I don't know if you can see here, we've got, I'm going to write in yellow. Okay, we've got a change in frequency over frequency, and this is from the AQA data sheet, but it's approximately equal to, on the OCR one, delta lambda, so that's the change in apparent wavelength over the wavelength, and v is the velocity of the source as opposed to c, which is the velocity of light. And again, on the OCR data sheet, those are approximately equal to instead of equal to. And the redshift is this ratio of speeds. And I want you to notice the negative. So the negative sign for redshifts, and they're given the symbol Z. I don't know why, but they are. The fact that it's red tells you that the source is moving away. Okay, so effectively all the redshifts, you just use the modulus of Z, and the modulus is the mathematical meaning of the word modulus, which is just disregard any sign in front. So the word red means basically that it's negative. So we always refer to positive values of redshift, even though the source is moving away. So if the source was moving towards us, then technically the redshift would be positive. But you just use the modulus, so you always use, so you talk about redshift, and if it was blue shift, if the source was coming towards you, then you would call it blue shift. Okay, nearly everything, not everything, but nearly everything is shifted towards the red end of the spectrum. Okay, so that is that tells you that pretty much everything is moving away from you. Okay, there are one or two things, especially in what's called the local group, that are moving towards us. So, for example, the Andromeda galaxy, which is our nearest neighbor, is a galaxy similar in size, probably a bit bigger than the Milky Way. That's coming towards us, but you don't need to panic. It's not going to arrive for another 200 million years, and I think that all of us will be gone by then. So pretty much everything except stuff in the local group is moving away, and so it has redshift. And the reason that we can tell that the wavelengths are all moved is because, for example, hydrogen has a certain pattern of lines and gaps and lines and gaps because of the energy levels in the hydrogen atom. So we can spot that pattern pretty much in any star, and we can see whether or not it's been shifted one way or the other, and they've all been shifted towards the red end. So they're all the wavelengths are longer. because the most of everything is moving away from us. Now, if you are doing the astrophysics option of the AQA course, then the Doppler effect, they bring it into binary stars. So I want you to think now about a binary star. If you've got stars going round each other, if they are sort of in the horizontal plane going round in circles, so that you actually look at it like stars separating and then they go in front of each other, and maybe they don't get far enough apart that you can actually tell that they're two stars, but you end up with it going brighter and dimmer depending on which star is brighter and which one's in front. And but you can have a look at the Doppler effect of those stars, because when they are moving towards and away from you on their way round in their circles, the waves from those two stars are shifted. And so you can tell from how much it's been shifted what the absolute speed is of the star going around the other star. So you can just look at the difference in speeds between them. So you can get the linear speed for the circular motion, and from the brightness, you can work out from the temperature. You can work out how uh, massive they are using Stefan's law. And so you can then use circular motion and the force and the radius. You just use V as R omega to work, and from the period of the, because one of them will block the other one out. So you can work out what the period is. So you can work out how far apart these things are from the redshift of the light, so, which gives you that linear speed, and the period from the occluding, occlusion, occlusion, or it's when one star goes in front of the other, and so you don't get the star bright, the light from both of them, you only get it from one, and yeah, so it goes dimmer briefly as they go past each other. So you can see the period, you can then work out the radius, so how far apart they are, which is very cool using the Doppler effect. Right. Hopefully we will come to a question on that if we get a minute. Hopefully, fingers crossed. Right. So that is the Doppler effect. It's the change in frequency and wavelength because of the speed, recession speed, nearly always, of the source of the waves. Okay, so that's the Doppler effect. Right, next bit then, in terms of cosmology, is Hubble. So we have been thinking about the whole universe, and Hubble, Edwin Hubble, he noticed a link between distances and redshifts, basically how fast things were going. And he invented this law, okay? And this is the law that he invented. That's Hubble's law, okay? Where V is the recession velocity, H naught is his constant, so it was just a constant of proportionality, and D is the distance. Now, we've just been talking about redshift, this Doppler effect, but with light. And that gives us V. So actually the recession velocity, relatively easy to measure. The distances, however, are incredibly difficult to measure. And the consequence of the distances being difficult to measure, because you can't take a ruler out into space and work out how far away any of these things are. I mean, basically, on the galactic scale, we haven't moved from home. You know, the furthest any man has been is just the other side of the moon. You know, we haven't even been there for like 50 years. So it's horrible, really, to think about how can we measure distance. Okay, so this is a really difficult problem, and the two that you're expected to know about is Cepheid variable stars and type 1a supernovae. So these are what are called standard candles. Okay, right, now a Cepheid variable is a star that is effectively breathing. When we think about the way that stars formed, what you learned in your GCSE is that a dust and gas cloud collapsed in under gravity. And when it collapses in, it gets hotter. That's gravitational potential energy turns into effectively kinetic energy of the particles. The particles are moving faster, they're hotter. They get hot enough, if it collapses enough, then they're going fast enough that when they collide with one another, they fuse, and bing, the star lights up. And that is how we get stars. Now, the star lighting up, nuclear fusion going on, means that the center of the star stays hot. And the fact that the particles are hot, they're moving fast, they bump into each other more often and harder if they're going fast. That radiation pressure, because it's hot, is what holds the star up, and gravity pulls in. So those two competing forces, this radiation pressure pushing out and the gravity pulling in, those are balanced in a main sequence star. Now, in a Cepheid variable, it's what's called a dynamic balance. So actually what's happening is that the star gets too hot in the middle, and it swells because of radiation pressure, and it gets too big and it cools down. And then, because it's a little bit too cool, it shrinks again, and then it gets hot, and then it swells and it cools down. And it does this. And it's a jolly good thing that our sun is not doing this, because it would be extremely unpleasant. It would get very bright and very hot, and then it would get cool and dark, and then bright and hot and cool and dark, so on. And but because of the period of going brighter when it's big to dimmer when it's small, that period depends on the absolute mass of the star. And if we've got an absolute mass for the star, we know what its absolute brightness should be at a fixed distance. So from the fact that some stars are doing this, and from their period, which we can measure, because we can see whether it gets brighter and dimmer and brighter and dimmer, we can know how big that star is, which means we know absolutely how bright it is, which means that we can work out how far away it is, because we get the intensity falls off of the square of the distance. So we can tell how far away it is. So our Cepheid variable stars, these ones that are kind of breathing, that will let us know how far away they are, which means that we can measure how distant they are. Now, most of the Cepheid variable stars that we can see are in our own galaxy. There are a few relatively nearby galaxies, nothing's near in space, but relatively nearby galaxies where Cepheid variable stars can be seen in other galaxies. Definitely in the Andromeda, but there are one or two others. I think M31 is one of them, and a friend of mine, Jane, she's been measuring them. It's amazing, actually. Anyway, Hubble saw some Cepheid variable stars in other galaxies, and this led him to his law. Now, Cepheid variable stars are just single stars, and they aren't specially bright. I mean, the Polaris, the pole star, is one of these Cepheid variables. The consequence is that when you want to measure very great distances, Cepheid variables are no longer any good, because they're simply not bright enough. We can't see the change in intensity of stars in very distant galaxies, because we can't see the individual stars. They're just, it's a smeary mess. So we needed something that was brighter that we could use as a standard candle. And a type 1a supernova is such a thing. Right, now, when stars form, there are there's a tendency to form binary stars. So It's got to do with conservation of angular momentum. If a gas cloud is spinning at all, when it collapses in, it spins faster. If it's spinning too fast, and it won't collapse right in. But if you've got two sort of smaller clouds that are going in kind of opposite directions, you end up having a conservation of angular momentum still, obviously, but you end up being able to form two stars more easily than you can one bigger one. And so binary stars are extremely common. I mean, possibly even more common than just single stars. And what happens is that stars go through their entire life cycle, and one of them might turn into, for example, a neutron star at the end of its life. But neutron stars, as I'm sure you're aware, extremely dense. So this star might pull stuff off the star next to it, and when it does, it pulls matter. You get what's called an accretion disk. So there'll be a disk of stuff that's spiraling in, and it gets bigger and bigger and bigger and bigger, and more mass comes onto this neutron star, and it gets all unstable, and then it goes bang, and you get a supernova. But the thing is, right, it's always the same brightness, because you always have the same amount of matter added to this neutron star before it goes bang. So you know how bright it is. And because how bright it appears to be, we can work out how far away they are. And they're much, much brighter than Cepheid variables. So if you can spot a type 1a supernova in a distant galaxy, then you can tell how far away the galaxies are. So we can use type 1a supernovae to work out how far away really much more distant galaxies are. And we can spot a type 1a supernova from how bright it goes. It's the shape, how bright it goes, how quickly, and how it tails off the brightness of the explosion kind of tails off in a certain pattern. It always looks the same. So we can tell which is a type 1 supernova as opposed to a type 2 or any other sort of supernova. And so we can use them as a standard candle. Anyway, so these two things, I mean, there are other ways of telling distances of objects, but these two allow us to do relatively nearby things, the Cepheid variables, relatively distant things, the supernovae, and we can use them as standard candles for measuring distances. Yay! Right, now, I'm going to show you the difficulty in just a minute with some graphs, but I want to talk about units. Okay, the best thing to measure the recession velocity in, of course, would be meters per second. In which case, the Hubble constant would be in per seconds, and the distance would be in meters. And then you've got a unified set of measurements, except that that's not what they do, because meters per second is very high. Hubble's constant number of seconds is enormous, and the distance in meters is ridiculous as well. Absolutely ridiculous. So they don't do this because the numbers are stupidly big. So what they do is they measure this is in kilometers per second. The Hubble's constant is in kilometers per second per megaparsec. And the distance is measured in megaparsecs. Mega just 10 to the 6. And a parsec, well, a parsec is, it's the distance where you get one parallax second of arc. So I am not going to explain what a parsec is now. I have already done that in a different astrophysics session, which I can put a link to afterwards if you want to, or you can look up how to measure a parsec on your own. It is, of course, in the AQA astrophysics teacher's notes if you want to look it up there as well. So they've got, right, can you see that there are a set of units that do go together, but it's kilometers per second, and it's the distances are measured in megaparsecs. So the Hubble constant is ridiculous. But what it means is that we end up with a sort of sensible number for Hubble's constant. I say sort of sensible because it's not really. The reason that I say it's not really is because the number that you are expected to use, and that's on the AQA datasheet, for example, is 65 kilometers per second per megaparsec. It's nowadays the accepted value is just under 74, 73.8. So it's out of date, basically. We're going to move on though, because what I want to do is I want to talk to you about these. I'm going to move that down a bit. These graphs, okay? Because Hubble invented this rule that said that V is proportional to D. The velocity is proportional to the distance. So the further away something is, the faster it's moving away from us. And he said it was a straight line, but I've just explained to you how difficult it is to measure distances. So these are real data. This is real data. So this, can you see the distance here? I need to pull up my thing. I'm going to go for red. Right, the distance here is in megaparsecs. Okay, and can you see we've gone up to 30? So it's kind of like here. It's down at the bottom. So this on the right here is just this tiny weeny itty bitty little bit for the local stuff down here. But look at the size of the error bars. They're enormous. Okay, right, now can you see this is 67 megaparsecs per kilometers per second per megaparsec, and then up to 83. Nowadays we think it's about 74, which is kind of in the middle here. The AQA says that it's a bit lower, so that would be down here. Okay, but can you see that the error bars get bigger and bigger and bigger and bigger in terms of the distance? Velocity, we've got a really good handle on because redshift tells us basically what the velocity is, but the error bar on the distance for the most distant objects, which are, you know, this far away, the error bar is enormous. Okay, so I mean, you know, that's a huge variation, possible distance. So I want you to be aware how uncertain we are about the Hubble constant. And I want you to be aware that 1 over the Hubble constant basically is the age of the universe. Okay, so it's really it's kind of fundamental to our understanding about the universe. This idea of Hubble and how difficult it is to measure, and how we are still trying to figure it out. Right now, I'm going to show you yet more graphs. Okay, so again, can you see here? This is 65. Okay, which is now at the very bottom end of our uncertainty, and we're saying that somewhere in the middle, 72, 73, 74 is probably around about right. And here, can you see the error bars? All of these here, the error bars actually do cross the line if we go for Hubble as 72 kilometers per second per megaparsec. Okay, here, this graph, I just want you to be aware, okay, again, we've got the distance in megaparsecs at the bottom, and we've got the recessional velocity up the side. And I want you to look at the uncertainty on these ones. Then the error bars are not big enough, basically. Our measurement of how well we're measuring things is not good enough on this graph. So I want you to be aware that these points, and I mean, I'm not even sure that these are error bars. Maybe they are, maybe they're not. But whatever they are, they're not big enough. The uncertainties are not big enough. We've got more uncertainty than that. And you can see that even for the nearby things that we're measuring the speed of, we've got fairly big error bars associated with the Hubble constant. Okay, I just want you to be aware of how difficult it is to measure things. Okay, and all the distant ones, these are all green. Can you see they're all with the supernovae 1A? Okay, they've got various methods of measuring things a bit closer nearby, which I haven't talked to you about, but I did talk to you about the supernova 1A. Right, okay, we're going to move on. Okay, so this is the teacher's guide. Okay, if I click on that, it should open it. Oh, it worked before. Have I got the teacher's guide up? Questions, teacher's guide. It was page 40. There you go. Okay, so on here, so this is the AQA teacher's guide. Can you see 65? And it's not. That's well out of date. Okay, it's about 73-ish, 73.8, I think it was, kilometers per second per megaparsec. That's the currently accepted value. I've got some data I was looking up earlier today from 2019. I think that's the last time they changed it significantly. So yeah, it's rubbish. This is rubbish, but you should use that in your exam. Okay, right. So there is Hubble's law. Right, clear my drawings. Close that. I need to go back to. Can I go back? Can I go back? I want to go back to that one. Okay, so so there is the data sheet on the right there. There is the data sheet. This is AQA data sheet. Okay, and this is what is the latest value. And I've realised I've almost halfway through my time. This is a NASA article, but I will make this presentation available to you afterwards. So you'll be able to click on that link and hopefully find that article if you would like to have a little look at that. Okay, going to move on. Okay, so so the Big Bang theory is okay. In the 1950s, there was controversy that said that the universe, well, there were two schools of thought. There was either the flat universe, where the universe is constantly being renewed and stuff is coming from we didn't know where, and it's being destroyed at the same rate, and the universe isn't getting any bigger and it isn't getting any smaller. It's what's called the flat universe, which was advocated by a famous man called Fred Hoyle, who wrote science fiction. As he was a professor at university as well. But the Big Bang theory was proposed, and Hubble discovered his rule. And this rule about the universe expanding led us to, if you go backwards in time, to thinking that, well, if the universe is getting bigger, then at some point in the distant past, it must have been all in one place. And it doesn't matter where you are in the universe, if the whole universe, everything is expanding, everything is moving apart from everything else. So, so this Big Bang theory was proposed, and Hubble's law, the evidence that he found from his expansion of his Doppler effect thing, his redshift thing, that is evidence for the Big Bang, because it shows that the universe is expanding. So, so the Big Bang is this physical theory that describes how the universe expanded, and everybody imagines, or at least I think they do, when they first hear about the Big Bang, when they're in, I don't know, year 10 perhaps. They think that it's kind of like an enormous explosion, but it's not like chemical explosion. It's not like a volcano erupting or something. The Big Bang, it's more the creation of space and matter and time. As far as we can tell, because we've got no evidence for it, time began at the beginning of the Big Bang. Maybe there was something before, but we've got no evidence. Maybe we could figure out some way of getting some evidence. Maybe eventually. I certainly haven't thought of anything, but that doesn't mean that it's impossible. It just means I haven't thought of anything, and neither has anybody else really. I mean, you know. But basically, it was the beginning of space and time. It was the beginning of matter, which of course is energy. And so this is it's just the beginning of the universe, and we now have more evidence for it. So there was this Hubble theory, but then there was the cosmic microwave background radiation. Now, the cosmic microwave background radiation was discovered by two guys. Their names were Penzias and Wilson. So here they are. These are the two guys, and they had a radio telescope, I suppose it was. They wanted to eliminate any background noise because they wanted to get rid of everything that wasn't radio sources from space. So they were trying to get rid of any noise, any rubbish in the background. They wanted it as quiet radio-wise as could be, so that they could spot dimmer and dimmer objects. Basically, that's what they were trying to do. And they discovered that it didn't matter which way they pointed their telescope, they always got this background hiss. Okay, and I'm going to play you. I've got it coming up next. This, if you turn the radio signals coming from space into a noise, which is what you do with a radio, this is what they heard. And it's constant. And it didn't matter which way they pointed their telescope. So this background hiss is, it's now known to be the cosmic microwave background. Okay, and so these guys, they tried to eliminate it. They thought that it was stuff from, you know, rubbish being absorbed by the electronics in their radio circuit, and they tried to they put them in Faraday cages, and they had boxes, and they eliminated everything. They, at one point, I mean, they had a radio dish thing. You can see it's not a dish, but they thought that it was pigeon droppings, guano, and they caught the pigeons and they sent them away. And then the pigeons came back because that's what pigeons do. And so then they had to shoot the pigeons. They got rid of all the guano. They cleaned it all off. Still they had this background stuff. And eventually they came to the conclusion that it was real, that it wasn't a manifestation of some mistake or problem in their equipment. It was real, and that it was coming from space. So now the cosmic microwave background radiation is now thought to be the very, very red-shifted stuff, red-shifted waves that have come from the Big Bang itself. So as soon as space became transparent and light waves could travel, they thought that those waves, which were of course in the gamma region, because at that point in the universe it was very, very hot, they've now been so redshifted by being stretched, either by thinking of space expanding, or you can think of the Big Bang, the edge of the universe are kind of moving away. It's been redshifted so much that it's now in the microwave range. And the microwave range of radio waves, they're radio waves really. I mean, microwaves and radio, well, where does it cross over? That indicates a temperature, because color temperature tells us that the hotter something is, the shorter the wavelength, the higher the frequency. The temperature of basically space is about 2.7 degrees Kelvin. So that's 2.7 degrees above absolute zero. So but basically there's this microwave background radiation, right? So they came up with this theory that actually they were looking at or hearing radio waves from the Big Bang. And so they sent up a satellite to have a look at it. And there was one before Kobe, but I'm not going to. So the Kobe was actually the second satellite they sent up to try to measure this cosmic microwave background radiation. And this one, whoops, I don't know if you can see my mouse. This one, let me make it yellow. This one is Kobe, okay, and that measured this. Okay, so and the bright and dark bits indicate the degree of what's called anisotropy, so how not uniform the background radiation is. And it's tiny. I mean, they milli Kelvin different across space. And this was the Kobe version, and then they sent up the WMAP, which is the Williamson microwave anisotropy probe, which is this one, and they measured this one, and you can see that they got much clearer picture of where the hot and cold bits are, but basically it looks the same in every direction. And they thought, right, we're going to have to go even better. And Planck, which is this one, measured it to an even finer degree. So, and it really doesn't matter which direction we look in, all of space looks the same. I mean, there are I mean, the difference between the red and the blue in the Planck one, it's micro Kelvin difference in terms of temperature represented. So it basically, space is the same in every direction. So our cosmological principle, which we started with, which said that space is the same in every direction, it really does seem to be true. But this is also, this cosmic microwave background radiation is also another piece of evidence for the Big Bang, because the flat universe theory can't explain this at all, and yet it seems to be there. And weirdly, from the relative anisotropy of the cosmic microwave background radiation, I learned in a relatively recent talk with the Bristol Astronomical Society that anisotropy within this can be used to measure Hubble's constant. And unfortunately, the value you get not within the error bars. So now, does that mean that the cosmological principle isn't quite right, and that things were different at the beginning of the universe to now? Don't know. Maybe it's more likely that our measurements just aren't good enough. But hey, this is how we discover stuff about our universe, which I think is absolutely fascinating. Okay, so cosmic microwave background radiation and the expansion of the universe from Hubble are the two pieces of evidence that you have to know about that leads us to the Big Bang. Right, so there we go. Now, interestingly, the evolution after the Big Bang is not part of the AQA option topic. It is in the OCRA course. So if you're doing OCRA, you need to have a little look see here. So this picture is a representation of what happens with the evolution after the Big Bang. And it is not to scale. Okay, I want you to notice things. Okay, so 10 to the minus 32 of a second is not a very long time after the Big Bang. And it was during this first 32 times 10 to the minus 32 of a second. I mean, it's a really, really incredibly short time, unbelievably short time, that what was just a point in space, which was space, expanded, sort of doubled over 90 times. Okay, and we had this enormous inflation. It's called inflation. So the universe, which was just a dot, became something that had a significant size. Okay, couldn't see through it. Okay, it was opaque. And after a microsecond, which is a lot bigger than that, protons started to form. Okay, now if you think about what's going on in a proton, we've got quarks forming, and presumably anti-quarks formed as well. That's a problem because all the antimatter seems to be missing. But anyway, we've got protons formed in microsecond, and then after a hundredth of a second, look at the scale. It's just rubbish. It's awful. After a hundredth of a second, we've got nuclear fusion beginning. So I want you to now think that, okay, so this universe is relatively small, although it's a lot bigger than it started. It's extremely hot. It's so hot that none of the electrons are joined to anything. And consequently, we've got this plasma which is conducting, and light can't get through something that's got charged particles in it like that. It won't go through. So you can't see through this universe. It's full of stuff. It's very hot. So it's the whole universe is like the middle of a star, and nuclear fusion is taking place. But during this period, and it only lasts for 20 minutes, look, nuclear fusion takes place. So we have hydrogen, the protons formed after a microsecond, joining together to make some helium and a little bit of lithium. Lithium is not, it's not commonly formed in stars. It's not particularly stable. The 4 nucleons together, 2 protons and 2 neutrons, is a much more stable arrangement. And consequently, lithium doesn't tend to form in stars. So we go from hydrogen to helium, and then lithium is skipped, and you do boron, and then carbon particularly, and then oxygen, and then and so on. So you tend to get, if you look at the relative abundance of elements, most of the lithium, we think, probably formed during the Big Bang, during this first 20 minutes. But the vast majority of matter at that point is in the form of hydrogen protons. So after 20 minutes, nuclear fusion ends. And it's not until for nearly 400,000 years later that the universe has cooled to the extent where the electrons are joining with the protons. And when that happens, you get neutral atoms. And when you've got neutral atoms, then light can get through. And so the universe is dark. So this is the dark ages, the cosmic dark ages. And it's not until the universe becomes transparent, then, okay, transparent. Oh, missed out the N. Transparent. Then that the cosmic microwave background radiation started on its journey. Of course, it was still very hot, but at least the universe had become transparent, and then light, all of the electromagnetic spectrum, all of those waves can travel now through space. And can you see that it wasn't until, well, it's about 4 billion years, it's not on this graph, about sorry, 400 million, not 4 billion, 400 million years, that's when stars start to form. So it's dark until the stars start to form. Okay, well, I mean, it depends what you mean by dark. It's hot, but dark. I mean, there weren't any stars. And then they start to form. And then the evolution of stars and galaxies and stuff, that's what's happened since then in the last, sort of 13 billion years. So we've got quite it's a condensed history at the beginning. Okay, so I'm going to clear my drawings and let's step on to the next one. So I've got, this is another representation. So you can see here is the dark ages. Okay, so we've got this dark region. Okay, so right from the beginning, nothing can be seen until here. Okay, and then we've got our first stars about 400 million years ago, and then since then we've got all of these galaxies. And can you see that this cone is getting wider? So this is indicating accelerated expansion of the universe. And as far back as we can see, there are galaxies. So we're now looking back into, well, of course, it takes light time to travel. So the further away the objects are that we're looking at with our telescope, the further back in time we're looking. And we can see back sort of over 13 billion light years. So that's 13 billion years ago that the light set off. That is almost the beginning of anything that can be seen. So at the end of this dark age. So I want you to be clear about what the stages are if you are doing OCRA, because you've got to be able to answer questions on this. So again, I'm not going. I mean, this is really, really sort of basic stuff. It's absolutely the minimum that you could possibly need. But basically, step one's the Big Bang. Step two is this inflation that happened in a very, very short period. And it's light elements are made. So this is when fusion is taking place, but it's very hot. It's too opaque. Then it cooled enough that it became transparent to light. And then we've got the emerging from that cosmic dark age, these clumps of gas that formed the first stars and galaxies. Then there is this idea. Now, this covers everyone. Everybody has to know about dark matter and dark energy, or at least the theory of dark energy. And we don't really know for sure that it exists. Dark matter. Vera Rubin discovered it. I think it was in the 1970s. That the stars on the edges of galaxies ought to travel slower than there's the stars in the middle, just because of circular motion, but they don't seem to. And that indicates that there is more matter present than the stuff that you can see. So she said that there's this dark matter, and so dark matter came into being in order to explain this. But what we think now is that there's more dark matter than there is visible matter. Of course, it's only the stuff that gives off light or reflects light that we can see anyway. We're now getting to learn about, and you don't have to know about this, but gravity is becoming a real source of extra information. So since 2015, when the first gravity waves were confirmed, we've now seen many hundreds of gravity events that were big enough for us to be able to detect. And I mean that, hundreds now. We're getting better and better at it. The LIGO or LIGO or LIGO, LIGO, it stands for Light Interferometry Gravitational Observatory. Those that they're being upgraded as we speak to become even more sensitive. But now we're getting more information from that, which is a completely different thing. I mean, if you think about it, all of the information we've got about the universe has come to us in the form of electromagnetic waves, because sound and stuff can't travel through space, and we can't go out to it to investigate it. So this is the only way we've been able to investigate up until now. We've got gravity, which is giving us a whole new insight into our universe. So I think these next 50, 100 years are going to be really interesting in terms of what gravity can tell us about our universe. She discovered this stuff called dark matter, which is basically matter you can't see because it's dark. But then Hubble discovered that not only is the universe expanding, but it is accelerating. The further away something is, the faster it seems to be going. So it's not linear. And it's accelerating. And so we've got this idea then of something pushing. And they've called that dark energy. Now, some people have said that it's Einstein had a cosmological constant. Well, he had two. One was for gravity and one was for anti-gravity, if you like, this pushing thing. And he said that it was his biggest mistake and that he shouldn't have introduced it to his equations. Well, now we're beginning to think that maybe we should have had it in there. Because we've got a universe that's accelerating away, and we have no principle which will cause this. So they've invented something which they call dark energy, which basically pushes matter. But we've got no mechanism for it. We have no model for it. It's very much still in the theory. Well, we've got some evidence that the universe is accelerating away. How do we explain that? So, somebody go into astronomy, please, and find out the solution to that. Maybe gravity will help us. I don't know. And then this step 8, it's not really a step. It's kind of like trying to find out more. So the James Webb Telescope it's like the Hubble telescope. It's looking at infrared though, rather than visible light. And I want you to think about the most distant galaxies. They are so red shifted that the visible light from them isn't really visible anymore. They've been shifted into the infrared. So James Webb will allow us to look further into the most distant galaxies, so we can look further back in time. And it also tells us stuff about potentially oxygen and things on exoplanets, maybe, because it's got some amazing interferometers on board. But that's information for another day. Right, okay. And that is it as far as me talking at you. So I do apologise for basically making this into a lecture. Um, Hello, can you hear me? I hope you can. Continue recording.
Yes.
Excellent. Okay, thank you very much. I think I pressed the wrong button. I do hope that I haven't lost that recording. But anyway, I was trying to close my share screen, and I think I must have pressed the end button. One is red and one is green. You'd think I'd get it right, wouldn't you? So right, I'm going to share my screen again. Actually, let me close that first because I want to escape from there. Right, share my screen. Right. Right. So I've got a bit over 5 minutes, and I pulled up some questions. Does anybody have any questions about what I've said so far? And I apologize for messing up at the end there. Has anybody got any questions? Because I'm happy to do that. Right, this was a mark scheme. I was going to go back to the beginning. Oh, come on. So these are just, well, I chose Hubble's law because most of what I spoke about was Hubble's law. Um, and this first bit I didn't talk about at all, but a quasar is a quasi-stellar object. It's the very large black holes, the really massive ones in the middle of galaxies, are absorbing matter because stuff is falling into them. And when things fall in, they accelerate on their way in. If you accelerate, you're changing energy, kinetic energy, and so these things emit light, and so they are really quite bright objects. Um, and that people think that they look like stars, but they're not really stars. So they call them quasars, which stands for quasi-stellar objects. So a quasi-stellar object or a quasar is basically a black hole absorbing stuff in the middle of a galaxy. And though they are also called active galactic centers, active galactic nuclei, AGNs. So a quasar is basically a black hole that's absorbing stuff in the middle of the universe, right? Of a galaxy, rather. But this next bit is about Hubble. So I need to have a darker color than that. Let's go with red. Okay, so we've got a distance in light years of a quasar. Okay, so it's in the middle of a galaxy, and it's got a redshift, and they've told us what the redshift is. So we've got Z is 0.0415, and remember that that is approximately, I suppose it ought to be approximately V over C, where C is the speed of light. Okay, so we can get the speed, the recession speed, V. And they want you to use it to estimate the age in seconds of the universe, right? So in order to do this, you've got to get Hubble constant, because 1 over the Hubble constant So Hubble to the -1 is the approximate age of the universe. So we're going to use this data to get Hubble. So V is H0D, that's the Hubble law. So we can say H0 is V over D. And V is this, so we need it in the C times 0.0415, and we want the distance. Well, we've got it in light years, but if I need to move that out the way, where is that's the specification. I want the data sheet. Have I got the data sheet? Data sheet. What we want, all of the option topics are at the end. Here's the astrophysics one. So what I want is the light year in meters. Okay, so 1 light year, that's a 1, is equal to 9.46 times 10 to the 15 meters. Okay, so I'm going to clear my drawing. No, I'm not. I'm going to just close that and go back to wherever I was. Was it that one? Yes, it was that one. Okay, so and my distance is, well, we've got, can you see? 5.81 times 10 to the 8 light years, and 1 light year is that far, so times 9.46 times 10 to the 15. Oh, I shouldn't put the meters in, should I? Okay, so, and I'm going to get rid of that C and multiply it by 3 times 10 to the 8. Now that is the Hubble. If we want the age of the universe, we have to flip it up the other way. Okay, so can we work out the age of the universe? Okay, so I get H0 as 2.27 times 10 to the -18. That's in seconds to the -1. So if I do 1 over that, I get the age of the universe in seconds. Look, they want it 4.41. I don't think we can really justify 3 significant, well, maybe 3 significant figures, times 10 to the 17. That's what I get. So, so that's the age of the universe in seconds. All right. Can everybody see how we did that? Okay. Right, clearing my drawings. So that was one. I've run out of time. That's about quasars. So evidence to support the Big Bang. Woo! Comes from the cosmological microwave background radiation and the relative abundance of hydrogen and helium in the universe. Okay, so so can you see this is a 3-mark explain, key fact, consequence. I haven't got time to do it. Okay, Brian is currently with us. So the catch up is going to be here, I assume. Is that your plan, Brian?
Hello, hi.
Hi.
Hi, say that brilliant. Enjoyed that very much, thank you.
Oh, thank you very
The
much.
catch
Right,
up,
I'm going to
yes.
stop sharing.
Oh, hold on. What I was going to do is start the catch up WhatsApp link. Shall I carry on with this?
I think not. I think we ought to go to the catch up, because otherwise somebody who
Yeah,
didn't
yeah,
come
yeah.
to this session because they're not
Yeah,
doing it.
Exactly.
We'll get confused. So I think that I'm going to have to end the session. So guys, if
Yep.
you've got questions for Brian, he's going to start catch up now, just 3 minutes late.
Yeah.
But you're going to have to leave and find the catch up link. All right, my lovelies. I hope you enjoyed that. I had fun. Bye.